Bismillah ar-Rahman ar-Rahim. Thank you very much, President. Welcome to my presentation. First of all, would like to thank the organizer for giving me this opportunity to give this talk on 3D modeling, printing, and bioprinting technology for the fabrication of radiation therapy bolus, human tissues, and organs. So I will be talking on 3D printing and the principles and the main application that are well established and the application which are also in progress. I will be talking also about a project that we are actually conducting in our laboratory concerning the fabrication of radiation therapy bolus by 3D printing. So first, I will give you an introduction by giving you the actual status and some definition and the main application of such technology in medicine. Next, I will provide you with some information about 3D bioprinting of human tissues and organs. Then I will give you an idea about 3D printing for the fabrication of radiotherapy dose bolus, which is the objective of our research projects, with some example of locally 3D printed radiotherapy dose bolus. And I end up with some conclusion related to the application of such technology in medicine. We start with the introduction. Here, the statement is here. 3D printing and bioprinting are revolutionizing various fields of medicine, offering new approaches to treatment, diagnostics, and personalized care. I start by 3D printing in medicine. So 3D printing is just, or also called additive manufacturing, is involved in creating three-dimensional object layer by layers based on digital models. In medicine, this technology has many applications. I give you here some application. The first application is the fabrication of prosthetics and implants. Thing which is very important in medicine. So here 3D printing allows the creation of prosthetics, limbs, tailored to individuals' anatomy, improving comfort and functionality. It is also used for patient-specific implants such as cranial pellets or joint replacements, and dental implants are now fabricated with such 3D printing technology. There are also other applications such as surgical tools and guide. Here, for surgeon can print custom tools suited for specific operation enhancing precision. 3D printing also allows the creation of surgical guides customized to the patient anatomy. 3D printing and bioprinting, 3D printing, is also can be applied for anatomical models and pre-surgical planning. Here, surgeon can print 3D models of a patient's anatomy, organs or bones, using data taken from MRI or from CT scans. These models are used for surgical planning, practice, and also for to train newly qualified surgeons. It can also used for drug delivery system. Here, there is the ability to create pills with a controlled release profile or combine multiple medication into a single pill and is an emerging application of 3D printing pharmaceuticals. Now we move to 3D bioprinting in medicine. Bioprinting is just a subset of 3D printing with a specific kind of ink that we use to print what you want to print. So bioprinting is just a subset of 3D printing that involves the printing of biological tissues and structures. It uses a bioink. A bioink is just a combination of cells with some hydrogel in order to print different things that we need to print. And here we use a bioink to create tissue-like constructs for medical purpose. I give you here some application. Some of these applications are still in progress, and others are well established. The first application concerns tissue engineering. So here we can fabricate artificial tissues. So researchers are using bioprinting to create tissues such as skin, cartilage, and bone for transplantation, which is a very interesting application, and also for research purpose. This tissue can be used to replace damaged parts or to study disease in a laboratory environment. Bioprinting can also be used for organ printing. Here, the ultimate goal is of bioprinting is to create functional organs such as kidneys, livers, or hearts from a patient's own cells. There is also another application which concerns wound healing and skin grafts. Bioprinting here is used to create skin grafts for patients with severe burns or chronic wounds. The process here involves layering cells and biomaterial to create a functional skin substitute that can integrate with the patient's body. There is also some application in cancer research. So here we can develop some tumor models. So here bioprinting is helping in creating 3D tumor models that are able to mimic the behavior of real tumor in the body. These models are used for drug testing and studying cancer progression in more realistic environments compared to the traditional 2D cell cultures. It can also be used for regenerative medicine. Here, bioprinting is critical in regenerative medicine as it can help to create patient-specific tissue to repair or replace damaged organs. For example, printing cartilage for joint repair is a promising application. For the future prospect concerning the use of 3D printing and 3D bioprinting, here I want to just to mention 2 points. The first one concerns the organ printing, which is an application still in progress. Here I want just to say that while still in experimental stage, the potential of 3D printing functional organs could solve the issue of organ shortage in transplantation, which is problematic actually. For the personalized medicine, 3D printing and bioprinting enable the development of a patient-specific treatment solution from custom drug formulation to personalized prosthetics and implants. So this is the prospect, the future prospect of these technologies. Now I move to the third part of my talk, which concerns 3D printing application in radiation therapy. So 3D printing also give many solutions in the field of radiation therapy. I give you some example of application. The first one is the fabrication of customized treatment planning. So 3D modeling allows clinicians to create highly accurate patient-specific model of tumor and surrounding tissues. This enables precise radiation dose calculation and optimizes targeting, reducing damage to healthy tissue. The second application is patient-specific mobilizing devices. So the fabrication of devices that are useful for the immobilization of the patient. So 3D printing can produce personalized molds and masks that help immobilize patient during treatment, ensuring consistent positioning for accurate radiation delivery. The third application is tumor and organ model. So here 3D printed replicates of tumor or organs allow physicians to visualize complex structure, improving the accuracy of radiation delivery. And the last application, which is the objective of our research project, is those bolus and compensator fabrication. Those bolus and compensator here in radiation therapy is just a tools used to modify the distribution of radiation, ensuring that it is delivered more effectively to tumor while sparing healthy tissue. I want just here to try to give you an idea about the different methods used in bioprinting. Because bioprinting is a new avenue that has shown a promise to alleviate the problem of organ shortage and transplantation and provide patients with a better quality of life. So let's start with presenting you the main method used in bioprinting. So here I'm asking you to watch with me this 6 minutes video, tutorial video, a very interesting one, and we come back to our presentation.
3D bioprinting, also just known as bioprinting, is a relatively new technology that, in theory, would allow humans to fabricate nearly any tissue or organ from scratch. The fundamental idea behind bioprinting is quite similar to that of ordinary 3D printing, in which a material, usually plastic, is printed, one layer at a time. Instead of plastic, however, bioprinters use bioink, usually composed of cells suspended in a special gel known as a hydrogel, which helps to protect, nourish, and hold the cells together. Some bioinks use a single type of cells, while others contain multiple types of cells, or multiple bioinks are used side by side, each with a different cell type. There are 3 categories of bioprinting that I will be discussing in this video, which differentiate in the method by which they turn the bioink into a specific shape. Note that due to the fact that this is an emerging technology, the exact name and classification of various methods vary from source to source. The concepts, however, are universal. I choose to group the various bioprinting methods into the following categories: extrusion-based bioprinting, droplet-based bioprinting, and energy-based bioprinting. Extrusion-based bioprinting is similar to what most people would think of when they think of conventional 3D printers. It involves forcing continuous filaments of a material through a nozzle.
So, the video,
also just known as bioprinting, is a relatively new technology.
The video is available on YouTube on this URL. So, concerning the challenge, bioprinting is now facing many challenges. I mentioned just here some challenges. The first one concerns the gas and nutrition exchange. The second one is about the biocompatibility of the ink that we are using. The third one is about vascularization, because we can 3D print a heart, but we get we are still the problem of vascularization. And the last one is the complex functionality of the printed tissue and organ. So these things are still under study. I want just here to give you just two examples about 3D printing. The first one concerns the fresh bioprinting lifelike heart model. The heart model is here is 3D printing. This application was developed by a researcher at the Finberg lab at Carnegie Mellon University, Department of Biomedical Engineering. They bioprinting a cardiac model that mimics the realistic feel, elasticity, and mechanical property of the cardiac tissue, and is also durable enough to handle suture and perfuse in order to use it for training. This is the first example of 3D bioprinting. The second example concerns the bioprinting of tissue for drugs toxicity test. Here, researchers from Wake Forest Institute for Regenerative Medicine in North Carolina developed a new multi-organ on chip to test the toxicity of the drugs. Here, 3D body on a chip could lead to faster and more economical drug development, as well as to reduce the risk of drug withdrawal after reaching the market. Here, this is the second example that was developed by this researcher. Now I move to the presentation of the part concerning the 3D printing of, for the fabrication of the radiotherapy dose bolus. As I told you, this is a project that is actually undertaken in our laboratory. So let me just explain you what is the bolus. The bolus is just a material that we put on the skin in order to get the profile of the dose, and especially Zmax. Here we have to get this Zmax on the tumor. So the maximum dose we have to get it on the tumor. Because we cannot change, even we change the energy of the X-ray from a value to another value. In some situation, if the tumor is near the skin, we cannot get the maximum of the dose on the tumor. So we add some kind of material on the skin in order to get Zmax shifted toward the surface. This is the objective behind the use of the bolus, which is just a material, equivalent human tissue that we use. But here I give you just a simple example. But generally, the morphology of the surface is not planar, so there is a lot of heterogeneity. So we have to print a bolus that fits well with the surface without any gaps between air gaps between the bolus and the skin. This is the objective behind the introduction of 3D printing in this for the fabrication of those bolus. Here I show you the conventional one. Here, this is the conventional bolus. As you can see here, there is gaps in both sides of the hand that causes the limitation of the conventional bolus. So the conventional bolus have many limitations for the use in radiation therapy. This limitation and inconvenience are particularly in terms of precision, patient comfort, and material properties. So the main limitation here for the use of conventional polish is the imprecise fit to the surface, the air gaps, as I told you, the disconform and movement, the limited reusability and consistency, and the skin irritation. So here, applying and adjusting conventional polishes to fit the patient properly may require additional time during each treatment session, affecting the overall treatment efficiency. So here we propose to use the 3D printing to fabricate such polish. So advances in 3D modeling, printing, and custom design can aid in the fabrication of polishes that address many of these tissue that I told you about by providing personalized, anatomically precise polish that fit the patient contour, exactly improving dose accuracy and patient comfort. The procedure that we develop to fabricate such polish with 3D printing, there is two phases. The first one is the shape definition and the polish sizing. This step is done by the clinician. So the clinician, depending on the treatment planning and the objective that he wants to achieve, so he define the polish, he define a polish, and he has the possibility to select the material. Here, very important thing, because we are using some material that are not in the treatment planning system, and if the clinician wants to, for example, to select any 3D printing material, the data must be included in the TPS. This phase was achieved by our team. So we include in the TPS two kinds of material that can be used for polish fabrication. The first one is the PLA and the GPU. Donc we characterize them and we introduce their characteristics into the treatment planning system. So the clinician now is able to choose such material as polish materials. The second, here I just show you how the clinician, with the aid of the medical physicist, define the polish. The polish here is in blue. So the example that you take here to show you is the polish corresponding to the nose. So the clinician here define the polish and select also the material that must be used for the fabrication of the polish. After that, there is the second step, which is the step of data extraction from the treatment planning system and the 3D model creation for 3D printing. Here there is 4 steps. First one, the polish data extraction from the TPS in DICOM format, then data processing by a computer-aided design in order to get a 3D volume that we can slice. The third step is the creation of 3D model of the polish to be printed, and the last step is the 3D slicing of the and creation of a printable STL format ready to be printed. Here I just show you the model created on nose polish. I told you that the clinician must select the material to be used for the fabrication of the polish. Here, this step was require characterization of the material. This step was done in the framework of our project. So here it is important if you want to use a new material to fabricate a bolus, to characterize this material in terms of radiological property, in terms of tissue equivalence, in terms of biocompatibility, in terms also of moldability, and in terms of stability. The material that we choose to work with is the polylactic acid, the PLA, which is a commercial available one. So, in order to introduce the data on this material to the TPS, a characterization must be done. The first one is concern the dose response. So, for the dose response, because we need the profile of the dose in depth, so we fabricate a phantom with some location inserts in order to introduce thermoluminescent dosimeter, and in order to measure the dose in depth. So we fabricate such a phantom just for this purpose, and in order to introduce the necessary data to the treatment planning system. Here I show you the printing parameter that we select to fabricate our phantom. Here, our phantom, and on the right, one kind. This is not the nose bolus, but one kind of bolus that we are studying. This is the 3D printing of the bolus. So when we finish the 3D printing of the phantom to be used for the dose in-depth checking, and also after that, if everything is okay, the bolus itself is printed. So let's move now to the presentation of the main results. So this is the printed phantom that you use to check the dose in depth of the selected material. Here, the result on this graph. In red, I show you the PDD of water, which is generally taken as a reference for the treatment planning, and the PDD, the dose in depth of the material that we select. There is a difference, certainly, because the mass density is not the same, but if you introduce the right data, no problem. For example, if you use water, we have, for example, 1 centimeter. 1 centimeter is equivalent to maybe 0.8 centimeter with our material to get the same dose shifting. So, from this first characterization, so we determine first the effective density of the used material, which is 1.17 gram per centimeter square. This is the effective value. We use it in the TPS. We determine the Z max corresponding to the maximum of the dose in PLA, which is 12.2 millimeter when compared to 50 millimeter in water. We determine also the ratio between mass density of PLA and water, which is approximately equal to the ratio between Z max of water and PLA. It is equal to 1.22. And we determine also the coefficient of equivalent thickness of PLA, which is equal to the same ratio, 1.22. And this coefficient is used to calculate Z effective corresponding to any thickness that the clinician define when he is using the PLA as bolus. So everything now is defined. We introduce these quantities in the TPS. We also check the enhancement value of the used material, because it is also a value that the treatment planning system needs in order to calculate the dose. Here, the enhancement units of the material used is about 128 HU. We print the bolus. This is the printed bolus using PLA as a material. We check the positioning of the bolus on the phantom, on the randomorphic phantom. So we check using CT scan. We check the well positioning of the bolus on the phantom. The first phase of our project is published in Technology in Cancer Research and Treatment Journal. So in this publication, all data on the characterization of the printing material exist in this publication. So the mechanical property, when the behavior of the material during 3D printing. So we publish in the first phase of our project the characteristics of the material that we are using to print bolus for radiation therapy. This is the dose response when considering CMV X-ray and 12 megaelectron-volt electron in both cases. So we characterize also the material in terms of enhancement units as a function of the in-file. So for the fabrication, generally we use 100% in-file, but if we need to change, so how the enhancement unit will be changing. So we study this, also this aspect. We check the surface roughness of the fabricated fabricated bolus. We check also the positioning of a different kind of bolus that we fabricate, and all this information are published in this paper. As a conclusion, I want just to emphasize the importance of 3D printing in many fields, particularly in radiation therapy, for the fabrication of different kinds of devices and tools that can help in the treatment planning in order to get accurate, precise treatment planning that ensure also some comfort to the patient. That's all. Thank you very much for your attention.